think yeah, mine here. Okay, well, people are still joining, but still welcome everyone. It's 11 here in Toronto and New York. It's 5 p.m., I guess, for our speaker. Thank you all for coming. Good evening, good afternoon, good morning, depending on where you are. So we have one announcement today. We have announced the call for papers for our winter session. So the information is on the Microstructure Exchange website, and you'll just go there, and the deadline is December 16. So we're looking forward to your submissions. Thank you very much. It would be great to see you all present. Well, maybe not all, but it would be great to see you come and present next coming winter. So today we have Sander Schwenk-Nebbe, and I apologize, I just butchered the name despite having tried it before. Thank you. So Sander, the floor is all yours. Sander has asked that you keep your questions to yourself until he makes pauses. So you're welcome to unload them during the pauses that he's going to make. And if unless there is a clarifying question, in which case, please raise your hand. The chat is also active. I will be monitoring the chat. And also the call for papers is in the chat right now, so you can just click on it and go directly straight to submit your paper. Thank you very much. Thank you, Sander. The floor is all yours.
Yeah, thank you very much for the opportunity to present this paper. The talk here today is about tech data, so the US equity market data that contains every trade and top-of-book quote update in US equities since 1993. A lot of universities provide access to this data set, either directly through NYSE Tech or through Words. Tech is famously the largest database Words provides access to. It is a great data set to work with, and I guess many of you have used it in some ways, perhaps, but there are some tricky parts to working with this data. And today I will, as the title implies, hopefully show you how you can get the most out of it. I would greatly appreciate if you can hold your questions to the designated break sometime mid presentation. After I've laid out the foundation of the paper, I'll take a break and then we can take some questions. All right, so the study that I'm presenting here today relies almost entirely on a new timestamp that is available in US equity market data. In 2015, at the request of the SEC's chair at the time, Mary White, a secondary timestamp was added to trades and quotes published on the US equity market data feeds. So now data feeds are a real-time concept, but tech data is nothing but the recorded, so the historical version of what is published on these public data feeds. So this implies that the second timestamp is also available in tech data. The second timestamp is set by each exchange's matching engine, and I will come back to that term later. The primary timestamp, which before 2015 was the only timestamp in the public data, is set by the entity that consolidates US equity market data from all exchanges. That timestamp reflects a point in time when a trade or top-book quote update is published on the given public data feed. So now the issue at the time, which is still relevant today, is that it takes longer to receive data from a centralized entity than directly receiving it from an exchange, however fast that centralized entity may be. And that is due to geographical distances between the exchanges, or better said, between the data centers of the exchanges and the centralized entities. If you have a server in the same data center as the exchange, data would still need to be sent to the centralized entity and back to you instead of you directly getting this data, but you could get access to this data without the round trip by just subscribing directly to the exchanges through their direct feeds, which comes at a significant premium. Now, having access to these two timestamps, you can measure the extra time spent between an event happening at an exchange and it being published or disseminated on a public data feed. This amount of time is known as dissemination latency, and as you can see, that was the intention of including this timestamp as it is written here. Issues raised in Easley, O'Hara, and Young from 2016 can with this now be studied. The first studies that use the new timestamp and go into this direction are Bartlett and McCrary in 2019 and Hashbrook 2019, which each in their own way quantify the advantage of subscribing to the proprietary data feeds over the public data feeds. But what I study here and what I present here in this study is a different direction. by revealing an important side effect of including this new timestamp. So what I find is that the new timestamp can be used to identify marketable order executions, or better said, we can use that timestamp, so the new timestamp, to identify for each marketable order execution the trades and top of book quote updates that were generated by it. So this is quite often critical information, and I will show that later. So as I mentioned, tech data is just the recorded version of the market events that are published on the public data feeds. In the interest of time, I'll only glance over the surface of the system's history here, just very quickly go through it. The request to implement a national market system, or in short NMS, and by extension then also the request to establish the public market data feeds, that one dates all the way back to 1975. In that year, the Securities Exchange Act of 1934 was amended due to, as they write here, advances in data processing and communication at the time. So they were certainly forward-looking when they wrote this law, that's for sure. The current system may very well be then as convoluted as it is, because it has evolved over such a long time. We don't have one, but we actually have two data consolidators, so centralized entities that receive trades and quote updates from the various exchanges, process that information, and publish the top of book and last sale info on the public market data feeds, which then again is recorded in tag. Those centralized entities that publish this data on the public data feeds are known as SIPs, or Securities Information Processors. And that term, as you can see, also dates back all the way to 1975. In the current system, if a security is NASDAQ listed, all exchanges will report trades and quote updates to the UTP SIP, which is operated at NASDAQ's data center in Carteret. So this I've drawn on this little map here. If it is not, so if it is instead NYSE listed, all data will be reported to the CTA SIP, which is operated in Marva in a different data center. I point that out because there are geographical distances between these data centers. So depending on the exchange at which an event occurs and where the given security is listed, information has to travel up to 57 kilometers or 35 miles to that centralized entity, where it is then processed and published and then again recorded in tag. When it is published or disseminated, it is timestamped with a so-called SIP timestamp. This timestamp is also known as time M in words tag or UTC sec in raw tag. Now, the second timestamp is assigned earlier because it reflects the point in time the event occurs at an exchange. It is known as the participant timestamp in tag, or part time in words tag. Participant here just means exchange. You can see the more formal definition up here from Reg NMS. So I know this is a bit convoluted, but we have now at least covered the two main terms, the SIPs and participants. So events come from participants and are timestamped there with the new timestamp, also known as the participant timestamp. And they are then processed at the central SIP. So sent to and processed at the central SIP, which is either the CTA or the UTP. And they are then there published on their data feed. And there they received SIP timestamps and are then finally recorded in tag data with those two timestamps. So now to the observation that sparked the study. Some time ago, I was working on quantifying the asynchronicity between trade and quote data and tag. That is a topic that has been studied for decades, and it's usually the same result, namely that trades are disseminated slower than quotes in US equity market data. So I was just wondering, how does the old issue look like today? I use a very simple methodology here. I gauge the proportion of trades that are traded at the prevailing bid or asking price. So the number of trades whose traded price equals the bid or ask of their prevailing quote over the total number of trades. So this proportion I report on the y-axis. I then offset trade relative to quote time when obtaining those prevailing quotes. That offset I report on the x-axis. So the blue bar here uses no offset, meaning the prevailing quote is obtained as the last quote update with an earlier timestamp as the trade. So that's just a standard definition. The bar just to the left of that blue bar uses a negative 1 microsecond offset, meaning only quotes more than 1 microsecond before trades are considered prevailing. The bar just to the right of the blue bar uses a positive 1 microsecond offset, meaning quotes up to 1 microsecond after trades are considered as prevailing quotes. Now, of course, we have two notions of time here now. We have the SIP and the participant time. I do this first in SIP time, as is displayed here. Now, what we see is that if we subtract time from the trade's timestamp, so if we move to the left of the blue bar, we have a higher agreement between trades and prevailing quoted prices. This could mean that quotes are reported earlier than trades in tech, or this could also mean that quoted prices move away from traded prices before trades are executed somehow. But the first is more likely because considering the article from Karen Colai from 2020, we find that lagging trade zip time relative to quote zip time does still improve trade signing today. And this is somewhat similar to the situation in Ready from 1991, but with a much shorter offset of than 5 seconds. But what really caught my interest is the difference in participant time. So in participant time, we don't see the same asynchronicity. In fact, the data appears to be perfectly synchronized, but that's not the key here. The key is that in no time at all, so if we just add 1 microsecond to the participant timestamp of trades no longer match with their prevailing quotes. And this directly implies that there are a lot of quote updates happening very close to trades in time, in participant time at least. And that is something worth looking into. Now, before we go to the results, I quickly have to cover the more boring stuff, namely the different data that I'm using here in the study. So the underlying issue I look on in the study is systemic, and that is because all data that is produced at the exchanges, so all trades and all quote updates, regardless of the security, receive that secondary timestamp, and all that data also goes through the SIPs to then be recorded in tech. So my aim is really to have a comprehensive sample of securities. My primary sample of tech data covers 2015, so when the participant timestamp is first reported, all the way up to 2021. I only exclude, and that is commonly done, securities that I cannot match with CRISP and securities that have a 0 market cap volume or a median traded price of less than $1 on any day in the sample. That leaves a large number of securities. So to keep computational costs low, I exclude all but Wednesdays in the sample. I include exchanges that were active throughout the entire sample period. Those exchanges make out 94% of all on-exchange trades in the period. So yeah, the final primary sample then contains 4 billion trades. On every day in the sample, I also partition trades in 3 market cap, dollar volume, price groups. So although this is a systemic issue, some securities may be more affected than others, and I want to capture that somehow. I use a couple of secondary data sources. I use 4 days of proprietary market data from NASDAQ and the New York Stock Exchange. I use intraday data on marketable order executions. Those were collected under the tick size pilot program Appendix B 2. And I also use daily data reported by the SEC. The proprietary data is publicly available as data samples, but it is order message data. So to compare it to tech data, we do need to parse it and convert it to last sale and top of book quote update data. Here I use the open source parser link below for the NASDAQ edge data, but for the New York Stock Exchange IF data, integrated feed data, I was not able to find one. So I just adapted the NASDAQ edge parser for that case. So the initial observation gave us a hint. In very short time, prevailing quoted prices move away from trades, at least in participant time, but not in SIP time. So what we do now is that we gauge the occurrence of quote updates in time around trades in that same security and exchange. So on the y-axis, I report the proportion of quote updates in a given bin over the total number of quote updates in all bins. So the bins, in other words, sum up to 100%. On the x-axis, I report the timestamp of that bin relative to the timestamp of that trade. So the bin at time 0 captures the proportion of quote updates that have the exact same timestamp as the trade. So now the timestamp is, of course, either the SIP timestamp or the participant timestamp. So the bin to the left of that bin at the center reports the proportion of quote updates with a timestamp 1 microsecond or nanosecond, depending on the figure, earlier than the trade, and so on. We have, unfortunately, both nanosecond and microsecond timestamp resolution because CBOE venues in the primary sample did not report at nanosecond resolution, only at microsecond resolution. Also, NYSE venues have no true nanosecond resolution, but report the participant timestamp with 256 nanoseconds frequency, which is a strange, resolution, but that's what it is. There's a drastic difference, as we can see, between participant and SIP time. In participant time, the vast majority of quote updates within the time frame have the exact same timestamp as trades. Note that the y-axis here is actually on a log scale. So with a linear scale, this would, of course, look even more drastic. So drastic, in fact, that you would not be able to see what happens around the peak here in the other bins. Yeah, for NASDAQ, for instance, let's take that one. More than 99% of quote updates that occur in the same security within those 2000 nanoseconds, so 1000 nanoseconds to the left, 1000 nanoseconds to the right. Yeah, more than 99% of those quote updates that occur within this interval have exactly the same participant timestamp as trades. In zip time, this is only 0.05% of quote updates that have the exact same zip timestamp as trades. So what is going on here? Before we answer that question, let's go to trades around trades and the same security and exchange again. So we do exactly the same thing where we just exchange quotes here for other trades, meaning that in the bin at time 0, we gauge how many other trades in the same security and exchange have the same exact zip or participant timestamp as trades. In participant time, we find something very similar. Again, take NASDAQ, more than 99% of other trades that occur in the same security within 2000 nanoseconds around trades have the exact same participant timestamp as trades. Now in zip time, we find something that looks very different. Across all exchanges, 0.00% of other trades, or virtually none, get the same zip timestamp as trades. So we have something that looks very interesting here. So how can we explain that? How can we possibly explain this? So we've now established that there's a clear difference between the zip and participant timestamp. So at the core, what differentiates the two timestamps is, of course, where they are assigned or who assigns them. The zip timestamp is set exclusively by the zips, and the participant timestamp is set exclusively by the exchanges, or to be precise, by the exchanges matching engines. And that follows from the definition of the participant timestamp, which we've seen earlier. So although the names imply this, to be sure, we can always consult the zips inbound protocol. So that is the format of the data that the exchanges send to the zips. Each zip makes this openly available on their website. The inbound protocol shows that the participant timestamp and only that timestamp is sent with each trade or quote update from the exchanges to the zips. The zips also report then that they set the participant timestamp to 0 if they somehow set it. So to know something about the participant timestamp, we really need to know what the exchanges do in their matching engines. Unfortunately, it is more than unlikely that we would ever get access to their code. But there are still some ground rules that an exchange's matching engine must follow. For instance, orders need to be handled sequentially in a given security, and the processing of orders takes a positive amount of time. I use here the paper from Aquilina, Budish, and O'Neill 2022, who show the structure of a modern exchange. The sequence of incoming orders is typically determined by a sequencer that relays these orders in sequence to the matching engine. The matching engine can only handle these orders in serial per security. There's just no other way. That means while one order is executed in one security, no other order in that same security can be executed. So the order book is effectively locked. I've typed down some simple pseudocode for this logic, which you can see here to the left. The message from the sequencer is received at the matching engine, at which point the order book in the given security is locked. So between locking and unlocking, no other message from that same security can be handled. Typically, messages between servers are exchanged in a binary format. So the message that is sent from the sequencer to the matching engine needs to be parsed before it can be handled. This and locking the order book and receiving a message all takes a little bit of time. So we have here the notion of positive processing time. After that, the message can be handled in what I here call the handle parse message function, or whatever that should be called. The first thing we do is to get the time and save it. This is the participant timestamp. For illustrative purposes, we assume here that the message is a marketable order. We proceed by executing the order, which means that for each resting limit order executed against, we generate a trade and we update the state of the book, which also results in a top of book quote update. This process also takes some time. So we finally return the market data generated by the execution and that single participant timestamp. The order book can then be unlocked and the next message can be processed. The key here is that while the order is being handled, no other order in that same security can be handled. Of course, that's clear, but this also implies that as long as the processing time is larger than the timestamp resolution, no other order in that same security can receive the same participant timestamp. Now we have, at least for some exchanges, nanosecond resolution, which at 1 billionth of a second is an extremely high resolution. To put things into perspective, how high that resolution really is, it takes about 10 nanoseconds on modern hardware just to begin reading data from RAM. Naturally, executing an order is much more complicated than just that. So under current hardware, and I guess in the foreseeable future, we can entirely rule out that a marketable order is executed in less than a nanosecond, again, in less than the timestamp resolution. This then implies that two marketable orders in the same security cannot receive the same participant timestamp, at least if we truly have nanosecond timestamp resolution. Now, returning to the SIPs side, after the exchange's matching engine executes the order, the generated market data is sent to the SIP. But the SIPs receive trades and quotes in separate messages. Again, we know this from the inbound protocol. We also know that those trade and quote messages contain no information about the originating marketable order. So effectively, information about marketable order executions is lost when a message reaches the SIPs. But this entire argument here, and I know it's a kind of a long argument, but it implies that we may be able to recover this information from the participant timestamps. And that is now what we are going to try and apply. So the first thing I want to do now is to see if our empirical findings are in line with what we've just established. So first, let's again look at the findings in participant time. It makes sense now that other trades and quote updates in the same security and exchange receive exactly the same participant timestamp as trades, down to the same nanosecond. Marketable orders are often executed against multiple resting limit orders, each time triggering a trade, and at the same time, orders do update the state of the book by consuming liquidity, each time updating the top of book. So in line with the pseudocode that I just showed, all of these events do receive then the same participant timestamp. So that is why we see these extreme peaks at time 0. So just to remind you again, the y-axis is still on a log scale on all of these figures. The order book in a security is locked while an order is handled. We also see that exactly. The proportion of quote updates and other trades around trades goes to 0 sometime before and sometime after trades. So this is the processing time at the exchanges. There's nothing here that we cannot explain with the logic that we've just established. We can even explain why the gap before the peak at time 0 is shorter than the gap after. This is actually also in line with the pseudocode. The matching engine receives the order, but has to do minor processing before it assigns the participant timestamp, for instance, parsing the message or locking the order book. And only after the timestamp is assigned, the exchange does the heavy lifting, which is to execute the order. So before we look at the clock, we have a little bit of time spent where the book is already locked. So in that time, we cannot do anything else. We then look at the clock and assign the participant timestamp, and then we spend some more time on executing the order, and then the next order can be executed. Now, of course, this is not visible in other trades around trades because that is by definition symmetric. So before one trade is after another and vice versa. So let's look at the SIP time. In SIP time, we have a drastically
Sander,
different
I know you said not to interrupt,
picture,
but just
that
in
is
case
also
anybody...
in line with what we've just
Sorry. Just in case anybody has a clarifying questions, perhaps we should pause because we have gone for about 25 minutes already. So normally we would have some pauses for questions, but I'm guessing everybody is very polite and waiting for you to stop. And since we only have 45 minutes, we're about halfway through. So just, did anybody have any clarifying questions? That would be your chance. Or any other questions? Sorry.
I have a question. If that's okay, Katja. I'm thinking about what we currently do when we match trades to quotes. And I think the recommendation in Holden and Jacobsen is to match the trade to the last quote in the previous millisecond. The millisecond
which is then later updated to nanoseconds.
Oh, has it been updated?
Yeah.
Okay. Yeah. So a millisecond would be an eternity on this scale. And can you tell us anything about how wrong that would be?
I will actually come back to that in a few slides, especially that topic, if that is all right.
Sure.
And if you could explain again the vertical scale on these graphs, I would appreciate that.
Yeah, so in the vertical, so these are bins. It's very difficult to see because those are, you know, in nanoseconds, those are 2000 bins, 2000 bins here. So the bin at time 0 is just counts. So let's see what we have here. We have quotes here. So how many quote updates in that same security and exchange have the exact same timestamp in this interval? So this interval in this case spans plus minus 100 nanoseconds, for instance, around a trade. So this, so each bin here will tell you how many quotes have that timestamp. So then the bin next to the one in the center would be the timestamp minus 1 nanosecond, the one left to that minus 2 nanoseconds, and so on and so forth. So this is just tells you how many of these quote updates within these 2000 nanoseconds, which admittedly is a short time frame, how many of these have a given timestamp compared to the trade. So that's why I used, oh, sorry. Okay. Perfect. So any other questions, or should I continue?
If there are no further questions, please continue. But if you have questions in the meantime, perhaps maybe raise your hand just so that we know where we stand. If there are sufficiently many raised hands, then Sander, maybe you can pause even if there is no scheduled pause, just so we we end it, because there's no co-author here to respond in the chat. True. So thank you.
So just to finish this this slide here, now I'm not exactly sure where I left off, but what we see in the top is that there are quotes now that do receive the exact same timestamp as trades. That is expected, because what happens is that the SIP actually does not stop. So there is no order book here. The SIP doesn't have to keep an order book, right? They just receive the trades and quotes from the exchanges. So they do not have to actually, they do not actually have to keep track of an order book. So what happens is then that quotes do not respond at all on trades. So what you see here at time 0 is that you see this suspiciously often that it's 0.05% here. And that is exactly 1 over 2001. So that just tells us that the quotes here are uniformly distributed in the bins around trades. So they do not respond on trades at all. On the other hand, what we see for the trades is that they do respond on trades. So why do the SIP respond on trades in the same security? The reason is just simply that they do have to process trades in serial. So these ones still have to be processed in sequence, but what you see is that they are handled one by one now. So in other words, there's virtually no other trade that receives the same SIP timestamp as a trade in one security. And that is an issue because we know from before that there are indeed many trades that receive the same participant timestamp. So a lot of trades happen at the exact same time, but in SIP time, this is not visible. Okay, I guess I can take that question right away.
Okay.
Your full name, sorry.
Simple, I know there's not a lot of them, but there are walk-to-book orders, an order that comes in, clears best price at a market, and then moves to the next price up.
Yeah.
Did you do any analysis on that style of order?
I come back to that because that is important for the New York Stock Exchange, which is a special exchange, as I would show. So all right, in a second, I will come to that topic. All right. I'm sure you wonder by now, and of course, rightfully so, why we need to go through all of this in such detail. Yes, I mean, the new timestamp is clearly different, but why is that even important? Well, the new timestamp really makes one thing painfully clear, and that is that the SIP timestamp is often problematic. The issue is simply dissemination latency, which is funny enough the primary reason for the existence of the new participant timestamp. So SIP timestamps are really just participant timestamps with dissemination latency added on top. Dissemination latency consists of network latency and processing latency. So network latency happens between the exchange and SIP, and processing latency happens at the SIP. Now, we may assume that the average transmission latency does not differ between trades and quotes, assuming they both travel over the same network, for instance. They certainly travel over the same distance. But average processing latency does not work that way. The SIPs do need to do different things with trades and quotes, and they also can choose to invest more in quote than in trade processing. Now, we don't have to speculate here in any way because the SIPs report their processing latency for trades and their processing latency for quotes. So when we go through their numbers, it is clear that trade latency is consistently higher than quote latency. So on the map to the right, I've drawn up a simple example of the issue this leads to. So consider the limit buy order that is submitted here at the New York Stock Exchange and is marketable because it can be executed right away against the single displayed resting limit order. So we assume that it is a single displayed resting limit order here that makes up the top of book on the traded side. We know by now that this triggers two events that will receive the same participant timestamp. It will trigger a trade and it will trigger an update of the top of book because it will consume that single resting limit order entirely. But the SIP timestamps, of course, do not necessarily reflect this. If we assume that transmission latency is equal, but the quote is processed faster than the trade, so that is a reasonable assumption, then the quote will appear in tech data as if it is prevailing before the trade. However, it is clear that the quote reflects the top of book after and not before the execution of the trade. So that is not a prevailing quote, it's actually the quote that comes after the trade was executed. So we will actually see that this kind of error happens very frequently. It's easy to see what happens in the data when we have the new timestamp, but without it, it's not as easy to see. And that's kind of the reason why we really need it. I will give two empirical examples now that make this very obvious. And after that, we can go through some questions. Then we've at least already been through the foundation of the paper. So in the paper, I give the following example of an erroneous sequence of trades and quotes. Now, of course, that is the first table in the paper, so it is to some extent cherry-picked to best explain the issue with sequence errors. But errors like these are by no means an exception in tech data. In the first panel, I arranged trades and quotes in Apple on NASDAQ in a brief period into sequence according to their SIP timestamps. Now, we look at the agreement between prevailing quote, trade, and subsequent quote update. There's only really one that makes sense, the one I marked here in green. That is the second trade, which seems to be executed against the prevailing top of book, reducing liquidity by the traded amount of 600 shares, so from 1,000 shares to 400 shares, and this makes perfectly good sense. The first trade also appears to be executed at the prevailing ask, but the quotes are subsequently updated at the bid side. This kind of shows how tricky the situation is because this may be wrong, so this may be a sequence error, but not necessarily so. It could also just be that the trade is executed at the prevailing ask, but at hidden liquidity and thus does not update the top of book. Then the subsequent quote update makes sense because it could just be an organic market response on the trade at the opposite side of the book. So the other four trades all appear to be executed at the mid quote in this case. So next we include the participant timestamp in the second panel. All of a sudden we know what happened in the sequence here. We know that we do have 6 trades, of course, we know that from the other one too, but we only have 3 marketable order executions because one marketable order was executed in 4 parts. The first trade we now correctly place in sequence before the quote update. It has triggered, which we see has incorrectly received an earlier SIP timestamp. So here we have a sequence error. So now we know actually that the first trade was executed against the visible top of book, triggering a quote update. We now also understand that the 4 trades were not executed at the mid quote. This is naturally important for trade signing. I will come back to that at the end of this talk. 2 of the 4 trades were executed at the visible top of book, updating it twice. The remaining 2 trades were executed against hidden liquidity. So we can check whether this is true in proprietary market data, which flags executions against hidden liquidity. And in this case, I do that. I confirm with my sample of NASDAQ itch data that these 2 were indeed executed against hidden liquidity. But I will also later show that we can infer this directly in tech data without using any proprietary data. I want to give a second example though. I recently came across a nice paper that includes a small sequence of tech data. So this time I let somebody else pick the sequence for me. is the paper from Aichaila and co-authors from 2022. They give us a small sequence of tech data where time here is the zip timestamp. The authors suspect that the third line of quote updates is caused by the fourth transaction. So I've marked those two with this little arrow. As we know now, we can check that. We can include the participant timestamp, and we indeed see that the quote update has received the exact same timestamp as the trade. It was indeed caused by the trade, which we now know. Again, we also see the making of a sequence error here because the zip timestamp of the quote is earlier than that of the trade, even though the trade caused the quote update. So yes, that is a sequence error. But now to go a little further with this example, I extend the table 2 with a few more trades that happened before and after. The old table is within the 2 big black lines. So using the participant timestamp, we can now see that the first trade in the original table was actually a part of a larger marketable order of 200 shares that was executed in 2 parts. We also see, if we move a few transactions down, that there is a large marketable order of 1,400 shares executed in 7 parts, and another one of 100 shares executed in 3 parts. Again, the new timestamp makes it painfully clear that the other timestamp, so the zip timestamp, is hiding what really happened here. The question that we do have to ask ourselves here is this: could we tell without the participant timestamp that the table does contain 3 marketable orders executed in multiple parts? One of them is a marketable order executed at 1,400 shares. Could we tell? That is difficult to answer. So I guess now I could take some more questions, but I don't see any raised hands, so I guess I can just continue. Otherwise, no.
Can I ask a question?
Okay, sure.
So this analysis appears to be directly at the, say, matching engine level.
Yeah.
So within the matching engine, I can see where you get all this alignment, but you're using historic data, right? So it's after the fact. So between market centers, there's still got to be some sort of lag. There's still transmission. In other words, if I want to take a look at the entire market, what would be the appropriate lags to put in place? I mean, within the matching engine, great, we can use a participant timestamp to align everything. But what's the lag between a trade and quote reaction at NASDAQ relative to ISE?
That is a good question. I guess I don't cover this topic all that much. The only thing that I do that is remotely related to that is to look at the relative NBBO. So that one is also from that Holden and Jacobsen paper from 2014. That one also shows us how we can get an NBBO that is relative to every market center. So then you take theoretical latencies and adjust the data ex post. So that is perhaps something that you could do or look into.
All right, thank you.
All right, next question, Albert. Okay.
Yeah. I just want to make sure I understood what you're saying, because your answer was different from what I was expecting. I thought you were going to say that you can use the inconsistencies in the clocks between the various participants and the SIP to identify where trades originated from, and therefore get them kind of sequenced correctly.
So can you maybe elaborate on that a little bit? I'm not sure how you would do that.
Well, you pointed out that there are inconsistencies in the clocks, which suggests that they're not synchronized perfectly. And so if there's slight errors in the way the clocks are synchronized, they should show up in consistent discrepancies between the participant timestamp and the SIP timestamp. And I was wondering if those consistent discrepancies would then be like a flag that allows you to align things better.
Yeah. So there's of course latency between an exchange and a SIP. Usually so there's usually geographical distance between an exchange and a SIP, unless the SIP is operated in the same data center as the exchange, which can also be the case. But then you still have latency, right, from processing at the SIP. So yes, you could take, in theory, you could use the zip timestamp and then subtract that latency from that timestamp, but you could also just use the participant timestamp that is already accurate. Or if your question more relates to having in real-time access to a latency adjusted NBBO, for instance, so that you know at this time I can get this and that information from all the other exchanges taking latencies into account, then that would be the relative NBBO again. So in that case, you can adjust the data according to the theoretical, at least, latencies. So that would perhaps one way to do it. Okay. Then I continue.
Sander, just one point. It's like it's 20 to 12. Our times. So we normally have about a 45-minute talk plus 15 minutes of questions. And I understand you have still quite a bit to cover. So just wanted you to be mindful of the time. So we have about 20 minutes for we happily stay till 12, but at 12 many people would have to leave. So if you have set of results, you should probably get to them before that.
Okay.
Thanks.
So one thing that I do is just as a final validation, I do replicate the proportion of hidden executions. And the reason why I'm doing this is because what happens in a marketable order execution, we can use that information. So in a marketable order execution, if a trade does not evoke an update of the top of book, then it must have been executed against hidden liquidity. However, unfortunately, in tech, that is not so easy because tech only reports round locked liquidity. So as I write here, tech data does not report odd lot quotes. So unfortunately, we cannot distinguish between an execution against odd lot liquidity or an execution against hidden liquidity, because both of them would not update the top of the book. Because again, in tech, we only see the round lot top of book. Regardless though, I can still get some information about hidden executions. And that is what I'm doing in this exercise. And I'm doing this exercise primarily because I want some sort of indication that the participant timestamp can be used as a marketable order execution identifier over the entire sample period. And what you see here is that we can indeed infer the same time series from tech. So the Securities and Exchange Commission releases this data, but they do source it from proprietary market data. So this data here, in this case, comes from tech. So the red line here comes from tech, and the blue one comes from the Securities and Exchange Commission. That they do not equal perfectly is very much an expected result. And the reason is that, of course, I cannot distinguish trades at less than 100 shares from odd lot or hidden executions. So I exclude those. So the SEC does not exclude those, and that is why we would expect that they are not perfectly equal, but you can see that the correlation is as high as 96%, I believe, here. And then the lowest one here is for Nasdaq PLX, which is also the lowest exchange or the smallest exchange, sorry, in the sample. Yeah. So now on to the next important thing. This is a very large figure that just shows the constellation of marketable order execution. So how many trades are grouped with how many quotes in that same security on the same exchange with the same participant timestamp. The most important numbers here, we can basically forget about the other ones for now. The most important numbers I've marked with yellow and green. Yellow being the proportion of all trades in the primary sample that occur with at least one quote update, and green being the proportion of all trades in the primary sample that occur with at least one other trade. So those numbers very quickly tell us how often does this actually happen? So how frequent is this in tech? And the simple answer, basic answer to that is very, very often. Across all exchanges, more than half of all trades have at least one quote update, one concurrent quote update. So a quote update with the same participant timestamp in the same security and exchange. Now, we know this is problematic because we know that concurrent quotes tend to receive an earlier SIP timestamp. So what we will find is actually that many of the quote updates triggered by the trades are placed in SIP time immediately before these trades. Now we can imagine that this can quickly become a large problem if we want to obtain prevailing quotes, because these quote updates here triggered in the same marketable executions are not prevailing quotes. They do not prevail before the executions, the marketable order execution. So similarly for trades, up to more than half of all trades, and that would be NASDAQ, have at least another trade with the same participant timestamp. So marketable orders are very frequently executed in multiple parts. But here, notice that the NYSE sticks out. Actually, if you just look at the shading, it's difficult to see here, but the New York Stock Exchange looks very different different compared to all other exchanges, and has a significantly lower number of trades grouped with other trades, which again here is marked in green. So is this an issue of the method? You could of course think that the method here just simply doesn't work for the New York Stock Exchange or something like that, but no, that's not the case. Some of you may already be familiar with this, but the New York Stock Exchange differs from the other exchanges, and we can by now trust our method. Our method's results also reflect this. So let me zoom in on the New York Stock Exchange and NASDAQ and explain what makes the NYSE special. In tech, but no longer in proprietary market data, the NYSE reports trades in the perspective of marketable orders. The SEC reported on this issue a while back in 2014, and there's also a recent paper from Upson and co-authors in 2021 that studies this issue. Our results actually reflect this exactly. Now, that trades are reported in the perspective of marketable orders does not imply that the number of trades paired with other trades should be exactly zero. So we find, as you can see, that 2.3% of trades are still receive the same participant timestamp as at least one other trade in that same security. This proportion, though, coincides exactly with the proportion of marketable orders executed at 2 or more prices for the NYSE. So what actually happens is that the NYSE reports one bunch trade per price level executed against. So not just one trade in total for every marketable order execution, but again, one bunch trade per price level executed against. So it is worth knowing this because, for instance, just comparing the number of trades between NASDAQ and the New York Stock Exchange is not sensible under these reporting procedures. And there are, of course, other issues as well. But it is also good to see, of course, that our methods reflect what we would expect to find. So that adds, of course, to the validity. So now I'm not sure, should I quickly go through the rest, or should we go to the questions right away, or how should we do it?
I would suggest that you would focus on the main results, because again, some people would have to leave in about 10 minutes pretty sharp. So, yeah. And I understand there are a number of results that based on the paper that you still have to. So maybe let's hold the questions. Sander has agreed to stay for about 15 minutes or a few minutes after the talk. But let's move to the implications of your findings.
Yeah. So very quickly here, then the implications at the BBO. We don't usually use the prevailing BBO. We usually use the prevailing NBBO. But anyways, we can start at the BBO, and what we see, what we can do there is just to obtain the prevailing quote as the last quote that had an earlier SIP timestamp as a trade. So that when we use SIP time, that's how we would do it. But what we can also do is we can use participant timestamp instead. So the participant time, meaning that for every trade, we look at the last quote in participant time directly before that trade. And that would be the prevailing quote. So if we do that, then we do see, of course, in SIP BBO, and now we already know that many of the quotes that are immediately reported before trades, they are actually caused by the trades. So those are not correct prevailing quotes. So if we use the SIP BBO and then compare that to the accurate prevailing quote in this case I get from the proprietary data, so from NASDAQ itch and New York Stock Exchange integrated feed data, then only 50% of those prevailing quoted prices, so for 50% of the trades in the sample, they yield both correct prices and depths. Only if we use the participant timestamp, we get to something that is very close to that, to the true data, 97%, so almost perfect prevailing quotes. Now, with odd lot liquidity, this is something else, but we cannot expect that from tech because tech does not include odd lot liquidity anyways. But there's a nice paper about this topic, and I don't have enough time to cover this, unfortunately. But just know this, even if we fix sequence errors in tech, odd lot liquidity is still a big problem. And that is simply not reported in tech. So now, of course, to the NBBO, which is much more important. So if we use the SIP NBBO, then we would use Holden and Jacobsen, as Hagström already said. But that one was updated indeed in 2018 to make use of nanosecond time steps. So as we can see, the way that we match trades and quotes with this method is by just taking for every SIP trade timestamp, we just take all the quotes that have an earlier SIP timestamp, so 1 nanosecond before the trade. And now we know that those quotes that we find in this way quite often are the wrong quotes, because those quotes are triggered by the trades themselves. So what can we do to fix this? We can use, as in Bartlett and McCrary, just the direct NBBO. So that is just the NBBO in force at the participant timestamp -1 nanosecond. So with participant timestamp, we don't have this issue anymore. But I want to be very careful with which sequence errors I fix. So I only fix sequence errors. So I don't exchange the SIP timestamp with the participant timestamp. Instead, what I do is I fix all DBBOs at every exchange and then compute the NBBO based on that. So I fix all of the sequence errors and then I compute the NBBO on that. So this is what I call fix NBBO. So now let's take a look at how often the fix NBBO disagrees with the SIP NBBO. So the fix BBO here, we've basically just looked at that. And that is, yeah, it's still a lot. It's about every third trade, or more than that actually, receives a different prevailing quoted price if we use the fix BBO. If we then use the fix NBBO, there is still more than 20% of trades receive an incorrect prevailing quoted price. So fix NBBO here is compared to SIP NBBO. So if fix NBBO yields a different price compared to the SIP NBBO, then we can be sure this is a sequence error because I'm correcting only sequence errors in fix NBBO. So that is something that you should know. If you use the standard definition and you use the SIP timestamps, you will quite often receive incorrect prevailing quoted prices. So these incorrect prevailing quoted prices, they do induce bias. And the question is, why would they do that? But let's just first use the SIP NBBO and the fix NBBO and compute the price impact at 1 second and 5 minutes, and the realized spread again 1 second, 5 minutes, and the effective spread, and then the imbalance weighted effective spread from Hagström. We just compare the measures using prevailing quotes obtained by fix NBBO, compare those to the measures we get when we use SIP NBBO. And what we see is that there is a very clear bias. In all groups, across all exchanges and groups, the price impact when we obtain it with fix NBBO is larger than that we obtain with SIP NBBO. And that is true for both the price impact of 1 second and at 5 minutes. For the realized spread, in all cases, we have that the fix NBBO yields a lower realized spread compared to the SIP NBBO. And for the effective spread, again, similar to the price impact, all of them yield a larger effective spread. So it is actually not so unsurprising to find this. And the reason is that, again, if we use SIP time, a lot of these quote updates that will be placed before trades, those are the ones that are actually triggered by the trades. So what I give here is just a simple example of a marketable order that is executed against 3 resting limit orders, each time generating a trade and a top of book update. So then we get 3 trades and 3 quote updates. So Q1, Q2, and Q next. So the key to understand here is that the difference between the correct prevailing quote and the quotes triggered by the marketable order execution is actually following the very simple rules of the order book. A marketable buy order can only immediately increase bid and asking prices. It can take liquidity at the ask, and it can provide liquidity at the bid when a part of the order is booked. But it cannot take liquidity at the bid side because it's not executed against that side. And then the same, or a similar thing counts, of course, for the marketable sell order, which can only decrease the bid and asking prices by taking liquidity at the bid and providing liquidity at the ask when a part of the order is booked. So that actually translates into a mid-quote bias. So bias and mid-quote that is contingent on the trade sign Q. If we have an active or marketable buy, then this mid-quote here with sequence errors, so if we confuse any of the 3 quotes here as the actual prevailing quote, this mid-quote will be larger or equal to the mid-quote, to the correct mid-quote. And then the same or similar again, when we have an active sell order, it's the opposite. So if we use then those quotes with sequence errors, those mid-quotes with sequence errors to compute the effective spread and the price impact, we do get a downward bias. So this one here is indeed smaller or equal to this one, and this one is smaller or equal to this one. So under these sequence errors that are caused by these quotes that are, again, caused by these marketable order executions and the SIP timestamps, I see it's a long kind of chain of things that has to work together. But under all of these circumstances, we do get a downward bias in effective spread, a downward bias in price impact. We also get biases in the realized spread and the imbalance weighted spread, but those are a bit more complicated. So the last thing I want to cover is trade signing accuracy. I have about 3 minutes for that, I guess. That is tight. So trade signing accuracy is, of course, very important. For trade signs, we do use prevailing quotes. I actually just use here the very standard lean ready method because I do find that to yield quite good trade signs. But what this is about is, of course, what happens to our prevailing quotes if we fix sequence errors? Do we get better trade signs? And I cannot answer that without having true trade signs in my primary sample. But my primary sample is tech data, and we don't have true trade signs in tech data. So it's a bit complex, but we do have 2 secondary samples that contain true trade signs. And that would be the proprietary data and the TSPP Appendix B2 data. Both of those contain true trade signs. So the first thing that I do is just obtain prevailing quotes with fixed NBBO, also direct NBBO, SIP NBBO with sequence errors, fixed BBO without sequence errors, but just using the BBO, and then SIP BBO again with sequence errors. And what we can see here, so let's start with this table here, we can see that we indeed get better trade signs when we fix sequence errors. So just compare fixed NBBO to SIP NBBO, and just ignore the RNBBOs. I cannot really cover those ones in time now. But just compare fixed NBBO to SIP NBBO. And then remember that SIP NBBO is the conventional method to obtain the NBBO with sequence, unfortunately with sequence errors. So we do get much better trade signs with fixed NBBO. And we have the same finding, very similar finding, when we use TSPP data. But unfortunately, of course, there are some major issues with just using those 2 data sources because they are quite limited. So TSPP data only covers those small cap stocks in the TSPP period. And the proprietary data that I'm using here is only for 4 days. It's only 4 days worth of data. That's not a lot. And the primary sample would be much better to use. So what I'm doing here is that I develop a very simple proxy for trade signing accuracy. And the proxy is average percentage price impact. So we know that on average, at least, that quotes are revised in the direction of trades. So price impact is actually quite well, a decent proxy for trade sign accuracy, because if we use the correct trade signs on average, our average price impact will be larger. Should I stop here? No. Maybe I have like 2 minutes more. Is that right?
No, please conclude. Yeah, no. So
concluding.
I didn't, sorry, I accidentally pressed the unmute button.
I saw it. And then,
but please go ahead and conclude.
Okay, sorry.
No, I didn't mean to interrupt.
So this proxy actually quite well covers the actual trade signing accuracy. So the proxy is just plain and standard average percentage price impact. We do use the 1 second price impact here. So that is due to Conrad and Bahal from 2020, who show that a short horizon in many cases is preferred. You can see that the trade sign accuracy is very similar to the proxy. So what I do here is I take every row of the table and I color it from green to red. So that gives us an idea of the distribution of these values within each row. So we have we have a very simple way of visualizing this distribution within each row, and then we compare that to the proxy for that same row. So for instance, take the first row here and then compare that to the first row of the proxy table. Now, of course, they are not going to be perfect. The price impact proxy for accuracy is not perfectly capturing the accuracy, but it gives us a more idea, and that is without using the true trade signs at all, because we do have but we do have the true trade signs in those samples. So I'm using those here. And as you can see, if we use the true trade signs, then we do get the highest price impact in all cases. So I'm marking those values in bold, but in all cases, if you use the true trade signs, you get the highest average percentage price impact. And that is also what you would hope to get for this method to work. So finally, let me apply it to tech data. And this is what we get. So we get something that is very similar to what we find in the TSPP data and the proprietary HNIF data. We find that after we fix sequence errors, we get a significantly larger average percentage price impact compared to SIP and BBO. And that is then again in line with everything else that we found before. So everything that I can show you here tells me that if you want more accurate trade signs, you should definitely take care of sequence errors in the data. Yes, okay, I'm gonna stop it here. Just extremely fast conclusion. So what we found is the participant timestamp is relevant beyond its intended application. And its intended application was to gauge dissemination latency, but we can actually use it for something else, and that is marketable order executions. Prevailing quotes from SIP timestamps are impacted. So now we saw that prices, and that's actually also biased, and as a result, central measures are biased, and trade signing accuracy is impacted negatively. So you should fix those sequence errors if you want to obtain the most accurate trade signs and the most accurate central measures. So what I presented here today is just a small extract of the paper. So if you want more information about this, then I would say, of course, you could read my paper, that would be nice. I also want to say, I really like this data set. It's a great data set. It has a lot of problems, but the participant timestamp seems to improve the data immensely. So there are many things that you can do with this marketable order execution identifier. I'm sure you can get some really great ideas that I have not even thought of. I have a few here, but I hope to see some more. That would be really good to see. Okay, now we can take the Q&A session.
Thank you very much, Sander. Sorry to rush you, but we do have also a lot of questions in the chat. Before everybody leaves, I just wanted to remind everyone that we do have a call for papers. The link is in the chat and also on the Microstructure website. Please submit your papers for the winter session. Thank you very much for joining, and we're happy to stay for the next few minutes to answer questions. Maybe it'll be faster if you have questions in the chat, if you just unmute yourself and ask it in voice rather than me reading the questions. Some of you have several, like Jim, Thomas.
Yeah. If there's an interesting implication of your findings here, and if I understood it, you're basically saying that the NYSE Classic system is reporting some trades as bunched trades.
Yeah.
That is basically one print to the SIP.
Yeah.
Whereas the NYSE ARCA system is doing trade shredding, which ARCA was doing even before they were taken over by the NYSE.
Yeah.
And now what this implies, if I understand the way the SIP revenues are allocated, is that the NYSE is not maximizing their take from the SIP revenue, because the way the formula works, one of the inputs to the formula is the number of trades based on volume, but it maxes out at $5,000 per trade. So any trades larger than that are really kind of wasted as far as the revenue allocation goes. So the either you found something that where the NYSE is not optimizing, or there's something else even more interesting going on. So I just thought I'd bring that to your attention.
That's a really interesting point. I could imagine, yeah, because maybe this $5,000 limit is relatively high, but it's not that high. It's a really good point. Thanks, that's really interesting.
I wonder, my guess is like Jim, what do you think the monetary value of that is? Maybe like 5 million a year that they might be missing out on maximum?
Oh, I don't know.
Because I think like their total share might be like, 50, 70 million. And I would guess if they turned everything that's currently capped into, 2 trades, maybe this is a few $1 million difference. And my guess is if they change anything about the data feeds, a bunch of their customers would be very upset, which might maybe be an economic reason for, why they're doing something not optimal, but aren't changing it.
Yeah.
Okay, the next question?
Yeah, Sander, maybe one question I had is, you highlighted that there are differences between large and cap and small stocks, stocks. Do you think that might be due to just the fact that maybe when there's widespread market activity, higher latencies, do people trade large caps more? Is that what's giving rise to that, or is there something else going on here?
That is something that I didn't look into, but certainly there should be a relation to latency. That is correct. So with a lot of trading activity, we should see a difference there. We should see perhaps even more sequence errors. But that is something that I indeed did not look into, and I wanted to cut the paper at this point because it's already at 80 plus pages. But I do think that there could be something there to be found. Yeah, that's a good point.
Now, do we have any good sense as to how accurate the participant timestamps actually are? That we know that the exchanges have their own requirements for clock synchronization, but how well are the requirements for the participants actually monitored?
How well they're monitored, I don't know. From what I can see, so if I go back many slides to the SIP time, they do look very accurate though, because what I find in SIP time. So perhaps I can just show that. It's quite far away. But what I see here looks very accurate to me. It's not very scientific to say that, of course, but they are timestamped down to the nanosecond, and this reflects very much what I would expect to see, because I do see again that there is some stop here. Then the SIPs are handling a trade, then they timestamp it, and then they continue. And this is extremely fast. So I cannot read this here, but what could this be?
Can you just check?
It's very fast.
Yeah. Can you just check the timestamp in the itch data against the participant timestamp in the TAC data? They should be exactly the same.
It's the
participant timestamp is supposed to be the timestamp from the matching engine.
Yeah.
So you can do. I mean, they should be exactly the same. If
they are
differ even by a nanosecond, there's a problem.
So the timestamps in the proprietary market data and the participant timestamp, those are the same timestamps.
Then the question is answered. The participant timestamps are the matching engine timestamps are exactly accurate.
Yeah.
Thank you.
But the question here was about the SIP timestamp. Okay.
So, Sander, maybe I overlooked it, but did you show that the bias is increasing with trade size?
Yeah, I did.
Okay. Sorry, I missed it.
Yeah, I did, because the larger the trade is, basically the larger the marketable order is, the more it will update quotes. So if it updates quotes more and you confuse then a quote from that marketable order execution as a prevailing quote, then that will lead to a larger error. So that you can indeed find that larger marketable order executions have larger errors.
Yeah, that makes perfect sense.
Hi, Sander. So my question is about how many proportion of your trade and quotes are actually misordered compared with the based on the SAP timestamp compared with the participant ID timestamp, especially for those quotes are similarly marketable orders in an exchange, because that's the essential part of the bias coming from, I guess.
Yeah, so the way that I quantify this is by looking at the disagreement between the prevailing quotes. So if you obtain the prevailing quotes in the old way or in the conventional way, the SIP BBO, so using SIP timestamps, then I compare how often those prevailing quotes differ from the ones that are obtained when I fix sequence errors explicitly. So that is what I have in this table here.
So this is a percentage, you mean? Yeah.
This is the proportion of trades whose prevailing quotes differ due to sequence errors.
Okay.
So I guess that is the proportion that you are looking for.
But especially for those, what the proportion between the marketable orders that you identify and the other, the other trades that may not be from those marketable orders?
Okay. So how often is this because of quote updates for marketable orders, and how often is this due to other
maybe
reasons?
limit order. Yeah.
Okay. There are certainly, so when you use the participant timestamp and you correct for sequence errors, I correct not only for those sequence errors that are caused by the same quotes within the same marketable execution. I also correct for all other sequence errors, right? You can also have that you have a trade, that one perhaps doesn't even trigger any quote update, but then there's a quote update short time after that trade. But due to the SIP latencies, again, that quote will still be recorded earlier than the trade. So then you have a sequence error that has nothing to do with a marketable order execution, modifying the top of book, just a quote that was updated after the trade and then is recorded before that trade. I also fixed those sequence errors. Unfortunately, in this table, I don't have the proportion of those, but in the paper, I do.
Yeah. Okay. Yeah. Thank you.
Thank you.
Any other questions or comments?
I have a comment. First, Sandra, I think it's a great paper, a very important paper. And
thank you.
I usually access the same data as you get from TAC through the Refinitiv history database. I know they have the same data source, so I thought that would be safe to do. There I couldn't find the participant timestamp. So that was interesting, especially as in the TIC history database for other markets, we usually get the one timestamp assigned by the database and another timestamp assigned by the exchange. So I think my impression is that this problem is specific to TAC to a large extent, and more generally saying to anyone that doesn't report an exchange timestamp. For most European data sets, I don't think we have this problem if we use TIC history. Currently, when we use TIC history for US data, we have a greater problem because we don't have the participant timestamp.
Yeah, that is an issue, and something that I also saw that I was not so actively aware of is that just if you go on the website on Words to download TAC data, then there is no participant timestamp. There you just have the time M, and then you would have to go to Words Cloud in order to get that timestamp. So that would something that I would like to have changed for sure, if I could ask for anything, because that timestamp, I think, as I say, in many cases is superior to the zip timestamp. You would have some very specific case. You would have to find some very specific cases where the zip timestamp is preferred over the participant timestamp. And I saw an interesting question from James in the chat. Should we as academics lobby the SEC to get trade signs included in the zip data? And I would absolutely would say that's a great idea. We should really have those trade signs. I always thought it was strange that we really still have to guess our way to those trade signs. They are so important.
And one academic in the wilderness doesn't have much impact, but if a lot of us actually started making this point, recently the SEC had a large consultation on what should be in the core data, and trade signs was not something that was brought up. And I'm embarrassed to say that I didn't bring it up in my comment letter, but I was thinking that we spend so much time and effort trying to guess the trade sign when the participants know the trade signs. So we should be making it clear that this would be very useful information.
Absolutely.
This is a little off topic, but a related proposal would be for every trade or quote that goes out to have a sequence number that can match the trade with the quote.
Yeah, that would be great as well. Then we might as well have a marketable order execution identifier that is kind of very similar. Then you would know which trade and quote belong together.
Yeah, it's just a matter of sequence numbers.
Yep, true.
Okay, so we're approaching 20 past the hour, so unless there are any other questions or comments, we probably will conclude. But thank you very much, Sander. It is a very interesting paper. And thank you very much, everybody, for attending and for coming up with questions. And we'll see you in 2 weeks.
Perfect. Thank you very much. Bye.